In this question, a scientist has 37.9 litres of oxygen gas, O2, and unlimited butanol, C4H9OH, at STP, that's standard temperature and pressure, and measures that 11.2 litres of carbon dioxide, CO2, is made. Step 1, let's balance our equation. So I'm going to set up a little table to see how much carbon, hydrogen, and oxygen we have in our reactants and products. So in our unbalanced equation, we've got C4H9OH. So that's 4 carbons, 9 hydrogens, 1 oxygen plus 1 more hydrogen. We've also got O2, so that's another 2 oxygens. So that gives me 10 hydrogens and 3 oxygens in total. Then in our products, we've got CO2, so 1 carbon and 2 oxygens, and H2O, so that's 2 hydrogens plus 1 more oxygen, which is a total of 3 oxygens. So to start with, it looks like our oxygens are balanced, but nothing else is. Since carbon only appears in one of the reactants and one of the products, I'm going to try and balance that one first. So I'm going to try putting a 4 in front of the CO2 and see if that helps to balance our equation. My reactants stay the same, but in the products, I now have 4 sets of CO2. So that's 4 carbons and 4 times 2, which is 8 oxygens. Plus I have H2O, which is 2 hydrogens and 1 more oxygen for a total of 9 oxygens. So now my carbon appears to be balanced, but my hydrogen and oxygen are not balanced. Now hydrogen again only appears in one reactant and one product, so I'm going to try and balance that next. I currently have 2 hydrogens in the products, but I need 10. So I'm going to put a 5 in front of the H2O in the products and see if that balances my equation. So I still have 4 CO2s, so that's 4 carbons and 8 oxygens, plus I have 5 sets of H2O, so 5 times 2, which is 10 hydrogens, plus 5 times 1, which is 5 oxygens, which gives a total of 13. So now my carbons and hydrogens appear to be balanced, but my oxygen isn't. I've got 3 in the reactants and 13 in the products, so I need to get 10 more oxygens in my reactants. So that's 5 more sets of O2. So I'm going to change this to a 6 over here and add up to see if that balances my reaction. So my products stayed the same, but in my reactants, I've still got C4H9OH, so 4 carbons, 9 hydrogens, and oxygen, and 1 more hydrogen. Plus I now have 6 sets of O2, so that's 12 more oxygens. So that gives me a total of 10 hydrogens and 13 oxygens. So finally, my whole equation is balanced. I can go ahead and put in my numbers. And same as every time on this platform, you need to enter a 1 on the website when you've just got one of it, even though if you were just writing down the equation, you wouldn't need to put a 1 there. Okay, great. Our equation's balanced. Now in this question, we're trying to find the percent yield. So we're going to need to know the actual yield. That's how much of the thing we actually got in the experiment. And the theoretical yield. That's how much we expect based on how much of our reactants we had using stoichiometry. So the actual yield is given to us in the question. The actual yield is how much we measured, which was 11.2 litres. So that's going to be our actual yield. So 11.2 litres, that's our actual yield. For our theoretical yield, we're going to have to use stoichiometry to figure out how much carbon dioxide should we have gotten if all 37.9 litres of oxygen gas reacted fully with unlimited butanol. So let's go ahead and do our dimensional analysis table. We're starting with 37.9 litres of oxygen gas. And just to figure out our steps, we're starting with litres of oxygen gas. We want to figure out litres of carbon dioxide. That's our goal. So our first step is going to be going into moles of oxygen gas. Then we can convert between moles of oxygen and moles of carbon dioxide using our chemical equation. Finally, we can convert that into litres of CO2. So we've got 3 steps in our dimensional analysis table. So step 1 is going from liters of oxygen to moles of oxygen. For that, we're going to be using the fact that we're at STP, standard temperature and pressure. Remember, at STP, 1 mole of gas takes up 22.4 liters of volume. So that's going to be our conversion factor for step 1. We're going to have liters on the bottom so that it will cancel out, and moles on the top since that's what we're trying to find. And 1 mole of gas equals 22.4 liters of gas. So that's our first step. Next, we want to convert from moles of oxygen to moles of carbon dioxide. So moles of oxygen is going to go on the bottom. Moles of carbon dioxide is going to go on the top. And if we look at our equation, 6 moles of oxygen produce 4 moles of carbon dioxide. So we can put those numbers in our table because we've got 6 moles of O2 reacts to give 4 moles of CO2. So that's going to be our conversion factor for this part. 6 moles of O2 reacts to give 4 moles of CO2. Finally, we're converting from moles of CO2 into liters of CO2. Again, we're at standard temperature and pressure and we're talking about a gas. So it's going to be 1 mole is equal to 22.4 liters. So 1 mole CO2 is equal to 22.4 liters of CO2. Okay, great. We've got our dimensional analysis table set up. So everything on the top is going to get multiplied together. Anything on the bottom is going to get multiplied together. We're going to divide top by bottom. So anything the same on the top and the bottom cancels. So liters of oxygen cancel, moles of oxygen cancel, and moles of CO2 cancel. So we're left with 37.9 multiplied by 1 multiplied by 4 multiplied by 22.4 liters of carbon dioxide. And we're dividing that by 22.4 multiplied by 6 multiplied by 1. So if we put that into our calculator, we're going to get an answer of 25.3 liters of carbon dioxide. That's our theoretical yield. So let's fill that in over here. Awesome. Okay, so we now know our theoretical yield calculated from stoichiometry, and we know the actual yield, what they measured in the lab. So we can use that to calculate our percent yield. Let's head to the reference sheet to find the equation for percent yield. Here it is. Our percent yield is given by the actual yield divided by the theoretical yield, all multiplied by 100. So for our percent yield, we're going to do our actual yield divided by our theoretical yield and we're going to multiply that by 100. So our actual yield was 11.2 liters of carbon dioxide divided by our theoretical yield, which is 25.3 liters of carbon dioxide, multiplied by 100. So if we put that into our calculator, we're going to get out a percent yield of 44.3%. So let's go ahead and fill that out to check we got it right. Awesome. Okay. So in this question, firstly, we're calculating our theoretical yield using everything we've done in this unit so far, using stoichiometry. Once we've got that, we're using it along with the actual yield provided in the question in the percent yield equation to figure out the percent yield of our product that we desire.